Electricity is everywhere. From the breathtaking spectacle of lightning strikes carrying thousands of amps, to the simple glow of an incandescent light bulb. If you were to pause and look around, it would be a challenge to find a corner of your environment untouched by electricity. As a matter of fact, the very device you're using to watch this video is a testament to electricity's omnipresence in our lives. We rely on electricity daily, using it to power our phones, computers, tablets, and even car stereos. Like an unseen force, electricity rules our world, an essential pillar of modern society we cannot live without. But, have you ever wondered how it all works? This invisible force, so vital, yet often taken for granted, operates according to principles most of the world overlooks. Imagine a glass of water with a straw. When you sip water through the straw, the pressure you apply draws water into your mouth. This pressure is akin to the voltage in electrical terms, the driving force that moves electrons through a conductor. In this analogy, the water flowing through the straw represents the electrical current, and the straw itself embodies resistance. Changing the straw's diameter illustrates how resistance affects current flow. A wider straw allows more water to flow with less sucking pressure, while a narrower straw requires more effort to achieve the same flow. As we embark on this journey to demystify the workings of electricity, let's delve deeper into a fundamental principle known as Ohm's law. This law lays the groundwork for our understanding of how electrical circuits function. At its core, Ohm's law elucidates the relationship between voltage, current, and resistance, three pillars that define the behavior of circuits. Once more, imagine voltage as the push that motivates electrons to move through a conductor, like a wire. This push is akin to the pressure you apply when sipping water through a straw. Current, on the other hand, is the flow of these electrons, much like the water moving through the straw. Resistance is what opposes this flow, similar to the straw's width, dictating how easily water passes through. Ohm's law states that the current flowing through the resistor between 2 points is directly proportional to the voltage across the 2 points. This means that if you increase the voltage, the current will increase as well, assuming the resistance remains constant. Imagine increasing the pressure with which you sip the water. Naturally, more water flows through the straw. Conversely, the law also tells us that current and resistance are inversely proportional. If we increase the resistance, imagine using a narrower straw, the current decreases. It becomes harder to sip water through, requiring more effort for less flow. This brings us to the concept of a voltage drop, particularly across a resistor. When current passes through a resistor, energy is used to overcome this resistance, resulting in a decrease in voltage. This decrease, or voltage drop, is a direct application of Ohm's law. The voltage drop across a resistor can be calculated by multiplying the current flowing through the resistor by the resistor's resistance. In your class, you will see this as V equals IR, where V is the voltage across a resistor in the unit of volts, I is the current through the resistor in the unit of amperes, and R is the resistance of the resistor, given in the unit of ohms. This principle is crucial for understanding how energy is distributed and used in a circuit, setting the stage for deeper insights into Kirchhoff's voltage law, where the sum of voltage drops around a closed circuit loop is always equal to zero. By comprehending these foundational relationships, how voltage pushes electrons, how current is the flow of these electrons, and how resistance hinder their passes, we gain a powerful toolkit for analyzing and understanding electrical circuits. This knowledge not only illuminates the path to grasping more complex phenomena like voltage drops across resistors, but also prepares us to explore the intricate dance of electrons through circuits, choreographed by Kirchhoff's laws. Kirchhoff's laws are divided into two essential rules, Kirchhoff's current law and Kirchhoff's voltage law. Together, they form a cornerstone of circuit analysis, allowing us to predict how electricity behaves in any given network, no matter how complex. First, let's explore Kirchhoff's current law, or KCL. KCL states that the total current entering a junction in a circuit must be equal to the total current leaving the junction. Imagine a busy roundabout in a city, with cars representing the flow of electrical current. Cars, or current, can enter and exit through various roads, or branches in a circuit. But the total number of cars entering the roundabout always equals the number of cars leaving. This law is a manifestation of the principle of conservation of charge, ensuring that in the realm of electrical circuits, no charge is ever lost or created out of thin air. Next, we have Kirchhoff's voltage law, or KVL. This law tells us that for any closed loop within a circuit, the sum of all voltages must equal zero. Returning to our analogy, if you were to walk around a park, starting and ending at the same point, the total change of elevation over your journey would be zero. You end up where you started after all. In the context of a circuit, KVL means that the energy supplied to the circuit by batteries or other sources is exactly balanced by the energy used up by the components within the circuit. The beauty and utility of these laws extend far beyond the basics, reaching far into the realms of more complex and dynamic electrical phenomena. Consider RLC circuits, which include resistors, inductors, and capacitors. These components introduce fascinating behaviors like resonance and phase shifts, phenomena that are critical in everything from radio receivers to filtering of electrical signals. Kirchhoff's laws are indispensable in analyzing these circuits, allowing us to understand how energy is stored and dissipated, and how signals move and change over time. Even more intriguing is the application of Kirchhoff's laws to AC, or alternating current circuits. AC circuits are not just about the steady flow of electrons, they're about electrons that oscillate, changing direction and magnitude with time. This time-varying aspect introduces complexities like reactance and impedance, concepts that are fundamental to designing systems that power our homes, our cities, and even our communication networks. While the principles remain the same, voltage around a loop must sum to zero, and current at a junction must balance, the presence of time-varying components in AC circuits adds a layer of complexity. Kirchhoff's laws help us navigate this complexity, providing a framework to predict and understand how these circuits behave over time. However, it is worth noting that these principles are not merely guidelines, but inviolable rules that the universe itself adheres to. This glimpse into the world of RLC and AC circuits is but a hint of the vast landscape of electrical engineering, a field where the foundational laws of Ohm and Kirchhoff guide us through the intricate dance of electrons in materials and devices of all kinds. These two laws, KCL and KVL, are the pillars of electrical engineering, allowing us to analyze and understand circuits ranging from the simplest flashlight to the most complex supercomputers. They assure us that, in the electrical universe, everything is accounted for. Every charge, every joule of energy. It's through these laws that we can harness the power of electricity with precision and predictability. Now, let's transition from the realm of theory into the tangible world of experimentation. To do so, we'll employ a few simple tools that are staples in the world of electronics: a breadboard, a multimeter, and, of course, resistors. A breadboard is a device for prototyping electronics. It allows us to create and modify circuits without the need for soldering, making it an indispensable tool for experimentation and learning. Think of it as a canvas for electrical engineering, where we can plug in components like resistors, much like an artist adds strokes to their painting. Resistors, on the other hand, are components that resist the flow of electric current. Remember our analogy of drinking water through a straw? In this case, resistors are like straws of varying thicknesses, each creating a different level of resistance to the flow of water, or, in our case, electrons. Resistors are given their resistance, or their thickness with straws, by their ohm rating. The higher the ohms for any one resistor, the more they will try to prevent current from flowing. They have more resistance. You can determine a resistor's ohm rating by looking at their unique color code. You can also, nowadays, look it up. And to measure the unseen forces at play within our circuit, we turn to the multimeter, an instrument that allows us to observe the invisible dance of voltage and current directly. With it, we can confirm the principles of Ohm's law and Kirchhoff's laws right before our eyes. We connect our breadboard to a voltage source and arrange 3 resistors in series. This setup will allow us to explore the fascinating principle that in any closed loop within a circuit, the net voltage around a loop is zero, a cornerstone of Kirchhoff's voltage law. As we connect our multimeter at various points in the circuit, observe how, despite the different voltages dropped across each resistor, the sum of these voltages equals the total current supplied by our source. This elegant balance underscores the harmony within electrical systems, a harmony dictated by the unyielding laws of physics. But our experimentation doesn't end here. By rearranging our circuit so that a junction is formed, where currents diverge, we can witness Kirchhoff's current law in action. Here, the multimeter will show us that the total current entering a junction is indeed equal to the total current leaving it, a testament to the conservation of charge. When measuring voltage, we do so in parallel with the component of interest. This method allows us to measure the potential difference across a component without altering the path of the current. Imagine observing a scenic landscape through a window. You're able to see everything clearly without being part of the scene. This is akin to how a voltmeter observes voltage, detached, yet providing a clear picture. An ideal voltmeter, in this analogy, acts like a window with an infinite thickness, so clear, yet imposing no influence on the landscape. Technically, this means it has infinite resistance, ensuring that it doesn't draw any current from the circuit and thus doesn't alter the voltage it's measuring. Conversely, current measurement requires us to become part of the circuit's flow, like stepping into a stream to feel its current directly. We achieve this by connecting our ammeter in series with the component or path whose current we wish to measure. This way, the electrons flow through the meter, allowing it to count them as they pass. However, this intimate engagement with the circuit's flow comes with a significant responsibility. An ideal ammeter behaves as if it were merely another piece of wire, offering no resistance to the flow of electricity. If an ammeter introduced resistance, it would alter the very current it aims to measure, like a dam reducing a stream's flow. But why is this distinction between measuring voltage and current so critical? Misplacing a meter can have dire consequences. For instance, attempting to measure current by placing the meter in parallel, as one does with voltage, could lead to a short circuit. This would allow a large amount of current to flow directly through the meter, potentially damaging the meter, the circuit, or worse, causing injury. This is why understanding the nature of these measurements and the characteristic of our tools, notably the ideal zero resistance of an ammeter and the infinite resistance of a voltmeter, is paramount. It's a delicate balance between observing our world of electrons without altering it and ensuring our safety as we explore. Through these experiments, the abstract concepts of voltage, current, and resistance become vividly clear. Our simple breadboard setup not only confirms the theoretical laws we've discussed, but also invites us to ponder deeper questions about the nature of electricity and its role in the universe. In this hands-on segment, we've seen firsthand how the principles that govern the flow of electrons underpin the technologies that power our world. From the smallest electronic devices to the vast networks of power grids, the laws of Ohm and Kirchhoff are omnipresent, guiding the invisible forces that animate our modern existence. As we wrap up our brief foray into the realm of electricity, it's clear that these principles are not just abstract theories confined to textbooks. These principles, although discovered in the 19th century, continue to illuminate the path of innovation, enabling us to harness the power of electricity with precision and creativity. As we ponder the future, remember that our journey into the electrical engineering universe is just beginning. With curiosity as our guide and knowledge as our tool, we stand on the brink of endless discovery, poised to unlock new technologies and solutions that can transform our world. Let this journey inspire us to look beyond the visible, to question, to explore, and to dream. For in the quest of understanding lies the true power to change the world. As we stand on the shoulders of giants like Ohm and Kirchhoff, let us carry forward the torch of discovery, lighting the way for generations to come.